In today's video, we are going to talk about Hello, George Romanic here. Welcome to Fundamentals of Weather and Climate playlist. In today's video, we are continuing our exploration of radiation in the atmosphere. And today we are tackling a fundamental question, childish question, but very important. And that question is, what would be the temperature of our planet if there was no atmosphere around our planet? In other words, we have our planet Earth as so, and approximately 150 million kilometers away is the Sun. We discussed this in my previous videos. Because the Sun is so far away, we can consider solar radiation that is approaching our planet to be parallel. Those solar rays to be parallel. Now, the first technical thing that we need to understand here is that only half of our planet is in daytime at any given moment in time, and another half of our planet is in nighttime conditions. In other words, only half of our spherical planet receives and absorbs solar radiation, and the other half is in nighttime conditions. Now we know that year to year, average temperature on our planet is not changing that much. So we are in the so-called steady state conditions. Temperature is constant on an annual basis. And that means that energy that we receive, energy in, needs to be equal energy that our planet gives back to the universe, namely energy out. Because if we were receiving more energy on an annual basis than we give out, temperature would increase with time. Or if we are giving out more energy than we receive, over time, our temperature would cool down. But that is not the case. So this conservation of energy formula has to apply. Now, what is the amount of energy that our planet receives from the sun per square meter? I have an entire video on that, and we know it is called solar constant, S, 1367 watts per square meter. And I put here star, you will remember in that video, because we said this is not exactly constant, it changes depending on the solar activity and few other factors, but for this video we take it as a constant. Now, what is energy in? Let's first discuss this. What is energy in that our planet receives? Well, that is absorption of solar radiation that we get. So this solar radiation, let's put it here in red, is absorbed by our planet Earth, and only half of our spherical planet that is oriented towards the sun receives solar radiation that I indicated here with red. But as you know from my previous videos, our planet also emits infrared radiation, also known as terrestrial radiation, and this emission, let's indicate it with the blue, happens in the nighttime part of the planet as well as in daytime half of the planet. So the whole planet is emitting energy out to the space, but only this part of the planet that is facing the sun is absorbing energy from the sun. And now when we know this, we can further expand this formula in the following way. Namely, what is energy in? Well, we just said it is this solar constant S. Amount of energy that our planet receives from the sun, but we have to reduce it for the amount of energy that our planet reflects back into the space. And I discussed that in great details in one of my previous videos. you remember that is called albedo. Approximately 30% of energy that our planet receives is immediately reflected back to the space. So we do not absorb 100% of solar radiation. And times what? Well, I just told you that only this part of the planet absorbs energy from the sun, and that is 1/4 of the sphere, and that is area of the circle, namely pi radius of the Earth squared. Because, in other words, if you want, solar constant is per square meter, but I now want to extend this to the whole area of the half of the planet that is facing the sun, and that area is pi radius of the Earth squared. And radius of the Earth is about 6,700 kilometers, but as you will see, it's not important here. So that is energy in. How about energy out? Energy out, well, our planet, is radiating energy in proportion to the temperature of the planet. And we know from my previous videos, then we use Stefan-Boltzmann's law, or Stefan-Boltzmann's law, sigma T of the Earth to power 4. This is amount of energy that a body with certain temperature radiates. Times what? Well, times again area over which this energy is radiated, and that's area of a sphere. An area of a sphere is 4 pi radius of the planet Earth squared. So you can see that these radii cancel, pi and pi will cancel, and we get that temperature of the Earth to power 4 is equal S 1 minus A divided by sigma times 4. Or we can finally put here that temperature of our planet Earth is equal 4th root of S 1 minus A divided by 4 sigma. Now, this is temperature equilibrium for these conditions. Now the question is, what is this temperature? Well, all these constants are introduced in my previous videos. I have a video that demonstrates that albedo of our planet is 30%, so 0.3, that's A. S, I just told you, is 1,367 watts per square meter. Sigma is Stefan-Boltzmann or Stefan-Boltzmann constant, and I believe is 5.67, something like that, check online, times 10 to power negative 8 watt per square meter per Kelvin to power 4. And what else do we have here? Nothing. So if you plug in these numbers, you will see that this equilibrium temperature of the planet Earth is equal negative 18 degrees Celsius. But something is wrong here. Something is wrong here, because we know that average temperature of our planet is actually about 15 degrees Celsius, positive 15 degrees Celsius. So we get discrepancy of about 33 degrees Celsius. What did we do wrong? What we did wrong is that we assumed there is no atmosphere. In other words, if our planet did not have atmosphere, the average temperature would be negative 18 degrees Celsius. But because we do have atmosphere, our average annual temperature is 33 degrees Celsius higher, namely 15 degrees Celsius. Why does atmosphere matter? That's what we are going to discuss in the next video. Until then, goodbye.